This is continuing with the introductory lecture of carboxylic acid. We left off with the nomenclature last time, and now we're going to look at the properties of carboxylic acid. To distinguish carboxylic acid by spectroscopy, you know already from Unit 1 that carboxylic acids is easily distinguished by NMR by looking for the OH proton, which shows up around 12 ppm, way downfield. And remember, because it's exchangeable, it's going to probably show up as a broad singlet. And in D2O, most likely you're not going to see it because it will exchange with the deuterium. All right, so that's one way to see this peak. And how would you distinguish that from an aldehyde, for example? Because aldehyde proton also shows up in 10 to 12 ppm region. You could distinguish that by IR because the carboxylic acid will have the carbonyl stretch around 1700, like the aldehyde, but then it will also have an OH stretch, which, as you know, is pretty big and broad, around 3000 to 3300 wave number. All right, so when you see both of them at the same time, you could deduce that you have a carboxylic acid, but you have to be careful if you're doing an unknown that your sample that you're doing the IR is dry and it doesn't have accidentally some water in it that's causing the OH stretch to show up. All right, so these are the peaks that you're looking for when you are you think you might have a carboxylic acid. All right, so carboxylic acids have C-O, so that carbon is an sp2 hybridized carbon, and then you have an OH coming off of that same carbon. So because it's sp2 hybridized about this carbon, the angle around them here, here, and here are going to be 120 degrees, right? About. And this atom, and this atom, the ones that are directly attached to the sp2 hybridized carbon are going to be in one plane. All right. Now, like alcohol, carboxylic acids are strongly associated with each other due to the hydrogen bonding. Notice that you have an OH group. And in fact, most carboxylic acids exist as cyclic dimers held together by two hydrogen bonds. So one carboxylic acid is faced this way, and the other one, if you do a flip, will have an OH this way, because then it allows them to have a double hydrogen bonding and exist as a dimer, or that just means two molecules that are existing together. And because of this strong double hydrogen bonding, it has a noticeable effect in the boiling point. Specifically, as you know, the boiling point is directly proportional, directly related to the intermolecular interaction. So you know that there are many types of intermolecular interaction. Van der Waals, you have the dipole-dipole, and of the dipole-dipole, hydrogen bonding is the strongest. So when you have a very, very strong hydrogen bonding interaction, the boiling point will be high, because in order for the compound to boil, it means that you're going from liquid to gas. So in order for it to do that, in liquid, the molecules are tightly interacting with each other, and in gas it's not. So in order for it to do that, you have to break apart all the intermolecular interactions that the liquid molecules have, and when they become separate, then it becomes in a gaseous state. So in this question, rank the following compounds in order of increasing boiling point. How you answer these type of question is that look at the functional group that is present. Octanoic acid will have carboxylic acid. Octanol will have an alcohol. Octanal will have an aldehyde. And octane is just all carbon-carbon. No functional groups present. So obviously this is going to be the lowest boiling point because it has the weakest intermolecular interaction, van der Waals, followed by octanol. So I'm going to put a greater than. So this is going to have higher boiling point than this because octanol will have an aldehyde functional group, and aldehydes will have dipole-dipole interaction with each other because we have a partially positive and a partially negative part in the structure. All right. So, but then the dipole-dipole interaction isn't as strong as the OH, because it allows hydrogen bonding. So remember, the hydrogen bonding only occurs to hydrogens that are directly attached to the oxygen or nitrogen or fluorine, and so octanol would have an alcohol group, and that will cause a strong intermolecular interaction, which is on hydrogen bonding. All right. Now, octanoic acid will trump that or have a higher boiling point because, as we went over here, it has usually occurs in a dimer, so it has a two hydrogen bonding interaction. So that cyclic structure that it creates is even harder. It takes more energy to break it apart than in an octanol. All right. And plus having that carbonyl and an oxygen, so it's got two oxygens. So there are two places where it could have hydrogen bonding interaction, all right, in one molecule. So this is going to have the highest intermolecular interaction, thereby having the highest boiling point, all right. So at this point, you should be able to do 21.3, which is mostly a nomenclature type of problem. All right. I'm going to move on because I don't think I'm going to finish the second one in time anyway. So I'm going to move on and do the introduction for the second lecture, which has got to do with acidity. All right. So you should be able to answer questions like this, where it asks you to circle the most acidic proton on the following structure and explain why you chose that proton, right? So when you look at a structure like this, you're going to look at all the hydrogens in an acid-base reaction to deprotonate. So here's a structure, a base coming in. Which proton will the base remove first, right? So we have many types of hydrogens here. We have OH types. So we have two OH types, one in here and one in here. One is an OH of the carboxylic acid, the other is an OH of a phenol type. And then we also have an NH type here. And then remember, I did not draw any hydrogens in, but all these carbons have hydrogens on them, right? So we have a CH type as well, okay? So in general, if you're just looking at the OH versus NH versus CH, you should be able to zoom in on one being more easily removable hydrogen than the other, all right? And that's based on the fact that these hydrogens are attached to different electronegative atoms. So we know that the oxygen is more electronegative than nitrogen. Nitrogen is more electronegative than carbon. So the hydrogens that are attached to different atoms, they're sharing the electrons, differently. So carbon and hydrogen, the electronegativity is pretty similar, so they're shared pretty equally. Nitrogen is more electronegative than hydrogen, so it's pulling electron density towards the nitrogen. But that scenario is happening even to a greater extent when hydrogen is attached to an oxygen. So we know that then, because this is not shared equally, this hydrogen already has some positive, partial positive charge. So a base coming in to grab it, and it has a choice of these 2 to 3 protons, is most likely going to get the hydrogen off of oxygen rather than nitrogen or a carbon. All right. So we initially answered that question: which of the following is the acidic? We know that it's going to be either this OH or this OH. All right. How do we know which OH is the more acidic one? Okay, that's what we're going to go over in the acidity of carboxylic acids. All right. So I'll conclude this lecture here because I'm not going to finish this next topic. So I'll start that in the next lecture.